is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hello, folks, and welcome to SkyTour Livestream. Mark D'Antonio here, and you'll never guess who's with me tonight, as if you didn't know. It's Daryl. Hey, Daryl, how you doing?
Hello, Mark. I'm well. I'm not well. I'm hanging in there. How are you? Hello, everybody.
I'm okay. I think this won't be as long as our other streams, but we're going to be looking at this guy right here. This is the Comet Olbers. And Olbers is going to be moving slightly south every night and heading eastward a little bit. And it's going to get fainter as it goes. So we're watching it tonight because there's something interesting going on. If you look at the telescope right there, it's really cranked over right there into the west, and you can see that we still have a sky glow there. And as the sky gets darker, we'll start to see more detail in here. But Comet Olbers is just exhibiting some really cool detail in its tail, and that's what we're after tonight. I want to say hello to the folks that are here, but go ahead, Daryl. I'm sorry to cut you off. Go ahead.
Oh, no. Go ahead. Say hi to everybody.
All right. I want to say hi to Renee Cruz, who was the first one here. Well done. Congratulations. And we have Tim F. Woohoo. Yep. That's his trademark. He always says woohoo every time he comes in.
Yep.
Every time. And we also have with us tonight Cosmic Ray so far. And we have Chris, who is Mind Forked in Oklahoma. And I've met Chris a few times. She's a real sweetheart. And love her to death. She's great. Don't be embarrassed now, Chris. And then we also have some other folks coming in here as well. With Christine.
Christine. So we have two Chris's?
Yeah. Well, the Mind Fork comes in as Mind Fork, but her name is Chris. And then go ahead.
Right. But Christine is not my Mind Fork.
No.
I mean, we have two Chris's.
Yeah, and you can see in the latest chat there, you see it says Mind Forked and Christine right below each other.
Yeah.
Yeah. So it's cool. Yeah. So this is Comet Olbers right now, and we're actually going to be looking at Comet Olbers to do something interesting. Well, not do something, but show us something interesting. Because right here, as time goes on, we're going to see the tail of the comet going this way, away from Comet Olbers. And so we're going to wait and see. It's got to get a little darker, all right? And then we can actually start to pull that tail out. Right now, we're just doing a 1 second exposure of the night sky right here. So we haven't actually done a stack yet. And we will. We're going to do that. I had an issue with the stacking software the other night. I couldn't get it to stack more than one frame, and I think I figured out what's going on. And I talked to the author of the software, and he's looking at it intently as well. So I will let you know how that goes. So we'll try a stack right now, and we'll do we're only gonna do like a 3 second stack, just because I want to make sure I can capture something even with the sunlight out. The sunset is occurring right now, so we'll make sure we capture. Yeah, let's see here. I gotta raise this up. This is my threshold for our full width half maximum exposures. This one should work. And there we go. So we'll have our first exposure. Yeah, it looks like that for sure. And we're going to clean it up right now.
Cosmic Ray may have stolen my thunder here, but yes, Comet Olbers. There's an amazing picture over at Space Weather. I'll post a link right now. The comet's ion tail took the shape of a corkscrew, and it's really amazing looking picture. If you click that link, and once the picture opens for you, you can click on it again. It'll get real big.
Yeah.
Beautiful picture. I have never seen a comet tail make a true corkscrew like that. It may just be an apparent corkscrew, if not a real corkscrew.
Sure.
Solar wind and CMEs, coronal mass ejections, have evidently hit the tail and disrupted it or reshaped it or whatever. That's a gorgeous picture, though.
Yeah, I'm looking forward to checking it out. And so let's see what we get. We have a lot of frames here trying to come in, but I've got to increase time and exposure to actually get a good one. So right now it's not detecting the proper number of stars. I'll just do alignment and just put this in. We'll clear it, do it again just to see what we get.
That first image I posted was taken on July 4. This next image was taken 2 days later, July 6th, and it's more of a landscape shot. Also a really pretty picture for. And it's another one, if you click on the image, it'll enlarge. Both are very nice images.
Can't wait. It's our stacking requires 15 stars, and it's unable to capture the others yet, probably because it's still a little bit light out, so it's not doing all the others. I was in here the other night doing a stack, right? It's stacked fine. Genghis is with us. Fantasy's with us. Nice to see you guys. Michael Hedrick is here. Nice to see you.
Hi, Isabella. Isabella's here.
Isabella's with us too. Yay. This is it right now. We're looking at Izabela. Waiting for it to get dark. So I'm going to come out of the stack here. We can't stack right now with it because it's not dark enough to do that. And then I'll come back to our low light shot here. That's a 3-second low light shot. All right.
On both those images I linked to, you can also see the dust tail closer to the head of the comet. It looks like it's fanning out, maybe almost about to make an anti-tail. Looks really cool. The dust tail is the broad fan down at the lower right around the head of the comet, and then the ion tail is the one pointing straight away from the comet, unless it's in a corkscrew again.
And the way that works, guys, is that comets are loaded with all kinds of compounds on their surface. They've had billions of years from the beginning of the solar system to acquire them and make new ones on their surfaces. And when a comet tail forms, as Daryl was telling you before, the dust tail is a separate fan shape, and that's actually just the material driven off the surface of the comet, because comets are very dusty. They're like Pigpen from the Charlie Brown show, Peanuts, right? Walking, you see a cloud of dust everywhere. Well, comets are like that. They're shedding stuff in their orbits, and it stays behind in their orbit. And once in a while, the Earth passes through a comet tail, and thus we end up seeing a meteor shower, and they're associated many times with comets, certain comets, you know. I don't know if you asked the question whether we're going to go through this comet's tail. I don't think so, but it is. It depends where they come. They have to cross Earth's orbit at some point or another. And this comet, I don't believe, is going to do that at all. So we're safe.
Yeah. If we see that dust tail form an anti-tail, though, it's not that we're passing through the comet's tail, but the dust tail, we would be passing through the tail's orbital plane, so to speak, which is what makes it look like an anti-tail. It looks like a spike coming out the front of the comet instead of behind it.
Yeah, it's all a matter of perspective. I want to say hi to Tiffany. Tiffany's with us. Hey, Tiffany. And Lubo over in China's with us. Papa Tom has just jumped in. Hey, Papa Tom. As it gets darker out there, we'll be able to see more detail in the comet here. While we're waiting, I'm going to actually do a nice focus run, because although I focused it manually, I didn't focus it electronically, and now I will. So we'll take care of doing that, and hopefully it's going to be dark enough to actually do that. What happened there? Yeah, that's what I thought. All right, so let this go. Oh, I see why it was doing that, because I wasn't at 1 second. I gotcha. Let me start that again and go to 1 second. It'll take longer this way. Now it'll be a shorter time, but I'll do it now. Okay. So let's pull that up. Do our 1 second shot. There we go. And let's start again. There we go. And hopefully there's enough. If there isn't, not a problem. I'll just move off the field. Alright, why is that saying that? Oh, I see why. Okay. Alright, let's try this now. Yes, as Izabela says, please hit the like button. Hang out with us tonight. It's a lot of fun. The images from the other night with the Omega Nebula and the Trifid Nebula came out beautiful, which I don't think you saw those yet because I did them in a private run with myself. I was just testing stuff. Look, it's using the comet head as a nucleus as a measuring point. I should have excluded it. Doesn't matter. There's too many others that are good. We're making a parabola down here, and once we see a nice parabola, it'll put a line at the center of the parabola. When it figures out the mathematical center, that will correspond to the smallest size stellar image. So you can see it forming right there. Mr. Django's here from Belgium. How you doing? Judy M is joining us. Hey, Judy. Nice to see you. Lubo says, shaved mark and orange hair. It's because I have my lighting on. There's the center point. And we'll let it go one more section. If you want, I can actually give us the, I can go full red if you prefer. Do that for a while. Okay, now we're fully focused, and I can get out of our focus routine. Telescope autofocused, we're good. Alright, and let's see now if we have enough to stack on. And I should have done this. Let's do a 5-second stack and see what that works, how that works. Okay. All right. Let's go here. Okay.
Izabela, I think Mark should grow back the mustache and the chin whiskers, the Van Dyke, It
Oh, the
makes him look like evil Spock.
No, it'll make me look like well, it'll make me look like all manner of typical scientist. Okay, it's getting darker. These are just showing us the stars we're stacking with. As you can see, we've stacked 7 with no errors, so we just needed to allow it to get a little bit darker. I'm going to color correct. And we'll get the tail here showing up. I will turn off the stars here in our stack now that I know it's working. So in the next stack they should disappear here. the next image. There we go. That looks nice.
Yes.
Now I'm only doing a 5-second exposure, right? Because it's not dark enough yet. If it gets dark enough, I'll be able to do like a 15-second exposure, and we'll start to see all the details of the tail. Let's see what we can see though. Let me push the processing artificially and see if we can see any data. Oh, you can see it out here. Wow, it goes all the way out there. Look at that. Oh, we're in for a good night. I should probably move it over.
Yeah.
So let's do that, guys. I'm going to come out of here for 1 second, and I'm just going to move this over. We'll go into low light mode again and move this to the east. All right, so we're going to do this. Okay, and then we're going to go north a tiny bit. Okay. All right, that's good. And now, as you can see up there, it says searching. We're looking for our guide star. And meanwhile, I'll set this up, and we're going to try and do a 12-second shot. See if we can get that regardless of the fact that the sun is still out. Not out, but bothering us. There we go, 12 seconds. Oops. Ugh. Alright, hold on. That's what I thought was going to happen. Okay, 12 seconds. Enter. Okay. So we got our guide star. We're guiding, as you can see right here. And now we'll come in here. We're going to clear this, and we're going to get rid of our low light mode and go into deep sky mode. Jane Murdoch is with us. Jane has been here at this location many times. She's a friend of the family. And let's correct the color. You can see the blue here already. Look at that. And let's try to pull that tail out from the background. Alright. We gotta wait for some exposures to come in. See, with the comet's always moving, so we don't want to take too many exposures. Plus, we still have the unfortunate blue of and red of the sunset that's affecting us right now. So we constantly have to color correct. Like that. Once it gets dark enough, we'll be able to take even longer exposures. Probably can do that now. Let's give it... We're going to do 20. 20 seconds. We'll start again.
I almost think I see tail running all the way from the comet to the to the left edge.
Yeah, it's very possible because I may have to go lower. Although I can zoom out a little bit more. All right, let's see here. Let's get this guy in now. Let's get our full width half maximum set up. Good, that's 7.7. And now we are... Yeah, you're probably going to see Comet all the way. I should go even farther to the right, shouldn't I? Let me just do this. Let me say fit the width. Yeah, I should put the Comet here. Okay, bear with me, folks. We're trying to get it right for you. All right. So that's what we're doing. Let's go into low light mode for a moment. Do a quick movement. Here we go. And we're going to move us here. I'm going to put us on a diagonal. That's probably that's as much as I want to move, because I'd like to capture whatever's here. The tail's right here, so we're gonna capture that. So let's go back to 20 seconds and get out of low light mode and head into stack mode again. Here we are. And let's clear this one. So Jane Murdoch, how are you? And PG is here. Hi, Petita. Petita in Pennsylvania. That's Pennsylvania Petita. How are you and Woody doing? C&D boys with us? Oh yeah, look at that. We're getting more tail here. And that Starlink. So I'm going to clear that. I don't want that in there. Sorry about that. It's probably going to be from here to here now. Yeah, okay. All right, we'll get there. One more clear. Stan from Two Rivers Observatory is with us. Hey, Stan. Nice to see you as well. There's a lot of interest in this comet, Comet Olbers. And, Comet 2023A3 is still out there. That's Tsutin Chen is still out there and visible. It's actually more east than this one. Oh, look at that blue tail.
Yeah.
You can really see that. And we only have one stacked image. When we get two, a lot of this noise is going to go away. Look at that. Oh, and guess what? I'm going to add an enhancement. I'm going to get rid of the color noise. Watch how much better it gets right now. Ready? Click. And boom. How about that? Now that's really pretty. Look at this tail, this bright blue line. That's really something.
And you can see the dust tail
Right here.
as a more separate form than what we saw
Right
the other
here,
night.
yeah. In fact, if you guys look carefully, you can see the dust tail very much as a separate object. We've got the ion tail right here in this blue, and then we have the dust tail. It goes to about here, and it's about as wide as this right here. All right, and it comes out of there. It actually maybe even more. It goes from here, it fans out. I'll do these lines and you just take them away. So it looks like it's doing this, okay, and then this, okay, and then the ion tail is right here, very obviously. Okay, so that's kind of what we're looking at. All right, let me try to bring that out by color correcting, get rid of some of the blue. It'll make the other blue stand out. There we go. Look at that. Now you see that blue tail quite nicely. This is a beautiful comet.
Izabela, I think I almost see a little bit of a crook on the end of the gas tail, kind of curving up toward the end of it. If that's related to the corkscrew or not. And if it's not just my imagination.
Well, you know what? We're only doing a 20-second exposure. I could do a 40-second exposure.
It might be a little early for that yet.
Yeah. 20 seconds is doing okay right now. So maybe a 35-second. But look at this. The more I do that, the better it looks. Let me try to push some of the data out here. What do we get? Oh, you jerk. That's the wrong comment. But yeah, Starlink had to pop through. Look, for all the detriments, Starlink, the Skyter live stream is brought to you by Starlink, right? So can't argue. Tiffany, how's Mike doing over at SpaceX? We haven't seen or heard anything of him lately, and we're getting very worried about him. He's submerging. Look at this. This is. Oh, really? I'm not drawing those lines.
Well,
Okay.
thanks, Elon.
Yeah. Well, that's why our skies, our commentary views are coming to us. That's the bright right there. That's really pretty. That looks really nice. Oh, seriously? Wow.
Well,
Whee.
I see a little knot in the gas tail.
Right here?
Yes.
Yeah, that's what I thought. Looks like it's separated. And that's due to probably the way the stellar wind strikes the comet's surface and it ionizes. Now, let's I'm going to clear this in a moment so we can do a longer exposure. One of the things that people might want to understand is what's actually being ionized and what does that actually mean. Well, I was mentioning before, the comet's surface is covered with all kinds of carbon compounds, okay, and many different ices, including ammonia ice, formaldehyde, carbon dioxide, water ice. But there's another gas that is on this comet, and it's carbon monoxide. All right, that's a molecule of a carbon atom and an oxygen atom, and that's monoxide, so carbon monoxide. And carbon monoxide, when it's ionized, works the following way. The electrons in that molecule's outer shell of the oxygen atom get popped off the atom, all right, and off the molecule, the atom in the molecule, and then when they come back in, they give off light. Well, the light in the carbon monoxide ion's particular case is blue, and so, and this is pointing to where the sun is. It's pointing exactly at the sun. This is the dust tail, which shows up very nicely here, and the dust tail is actually. Let me just pull this off the left peak here. The dust tail. I gotta do this. Okay, the dust tail is in the comet's orbit, as Daryl was saying earlier, and the ion tail just points away from the sun no matter what. Look at how far it's going. Very obvious now.
You know, I'm seeing quite a distinct kink in the comet's tail now. That same place down fairly close to the head of the comet.
I'm going to add a unsharp mask, which actually is going to add details. And so I'm doing that now. Let's see if that helps us. Oh, look at that. So you definitely see a separation here and there. There is it's definite separation. It's a brightening right there as well. So there's a denser number of these ionized molecules.
We may be seeing another corkscrew form, huh, Ray? There's that kink area. It's bright, and then it's kind of curving down again to the left.
Right there.
To where the ion tail is running away.
Look at this, another one.
Holy cow.
No. I'm going to save this anyway, just to have a record of how many crazy satellites went through. And this is going to be saved as Comet Olbers. All right, so now I'm going to clear it, and we're going to start again and see if we can get a clean shot without this. And we're going to actually go up to 25 seconds. Get us a little better ion tail view. All right, so let's just start it over. That's the previous one. We'll clear that.
So why is it called Comet Olbers? I know.
Well, tell everybody then.
I'm getting ready to.
Like Olbers Paradox.
It's named for Heinrich Olbers, who was an astronomer back in the day, German if I remember correctly. And Heinrich Olbers is famous for coming up with Olbers Paradox, as Mark mentioned. Well, what's Olbers Paradox? Olbers was pondering one night, and he said, "Why is the sky dark at night?" That is Olbers Paradox.
Yeah, the idea is that stars should be visible everywhere you look, if there's that many of them.
Yeah.
And unfortunately, what Olbers didn't know at the time, and may have suspected because he was a very smart individual, is that there is a fall off of the intensity of light by the square of the distance away from the object. Oh, look at that. Look at that. You can see these knots.
Yeah.
And that fall off in intensity is called the 1 over r squared law. So that means if you go twice as far from an object, the light is 4 times fainter. 2 squared, 2 times 2 is 4. And if you go 4 times further, okay, from an object, then it's 4 times 4, 16 times fainter. So when you look in the sky at something that you're looking at in the sky, you know, it's pretty bright for you to see it as you see it in the sky because the light would have fallen off by whatever distance it is. So they are pretty bright. But stars, being as far as they are, you would be able to see the light of a most distant star as well as the light of a closer star equally. And you just can't. And this is why I don't like taking pictures at the western horizon at sunset. But we have no choice, so we'll do this.
This Fantasy asked, why wouldn't it be dark? Fantasy, back when Olbers was around,
Good.
I think the supposition was that the universe was infinite still. And his reasoning was that, well, if the universe was infinite, any direction you looked, you should eventually come across a star in your line of sight. And if you shifted your view just the least little tiny bit to one way or another to the side, you would still see stars.
Oh, wow.
And therefore his idea was that the sky should be as bright as the surface of a star. That was his thinking. And the paradox is, well, obviously that's not what we see. So what does that say about the universe?
There you go. Hey, Sam S. Hello, Connie Quake. I like that name, Connie Quake. Connie, tell me you're a geologist, and I'll say that's a great name. Look at this tail. Look at how convoluted it is. And then we got this definite hook in the tail right here.
Yeah.
There was definitely a disconnection here at some point. Yeah. This might be the corkscrew part. Look at that.
It's, as Ray was saying, I mean, it's not the same corkscrew.
Yeah.
Because that was 4 days ago and it's long gone by now.
Oh, sure.
Although that July 6th image I posted earlier, it still did show up, except it was extended farther away from the head of the comet. I think if you look at that, the bright little arc we see there, there's a dark arc right in front of it.
Right here?
Maybe the disconnection event just immediately to the right of the bright part.
Oh, right here you mean?
It's darker there, yes. And
yeah,
also I think the tail looks like it curves down.
Yeah.
To the left a little bit.
It does. It looks like it goes down, but then look at this. We got this arc here comes down. Then you got this arc right here going out as well, and you got a darkening in here.
Yeah.
So there's definitely what that could signal is not a CME event or a change in the solar wind. However, it could change. It could, by the way, signify a change in the cometary outgassing that was occurring on the surface of the comet. Okay, so that could be responsible for what we're seeing. A disconnection event could be related to how much stuff can be ionized, how much of it is available to ionize. So it's possible that a large amount of that material that came off, maybe there was a lot that came off here and could be ionized, and maybe there's less of it, back at certain other points.
As Genghis said, could it be sputtering, the material
Yeah.
heating and cooling, question mark.
Yeah, absolutely, Genghis. That's a good way to put it.
If you look toward the upper left, there are 2 parallel satellite tracks, and one of them appears to be a tumbling rocket body.
Yeah, right here.
Yeah. See how it's bright and it gets dim and it gets bright again?
Yeah. Well, those are gonna go away too, as we add more proper data over them. Let's see here. Let's take this to the left a little bit. Wow, that's really cool. I'm liking it. I like it. Yeah, this is nice. Definite disconnection event going on right here. You can see this really sharp carbon monoxide spike here. Ionized carbon monoxide here. Jose Santos, hello. How are you in Lisbon, Portugal? Nice to see you, man. Thank you for joining us. Please make sure that you subscribe. We're free. And all the pictures we take will be made available to you. As example, I'm going to hit save right here. And this image is now saved as an astronomical FITS file. And then we'll save it exactly as seen. And that is a PNG. So what's up on the server heading up there is this image. And you're free to download it and do whatever you like with it. All right? So we actually provide these for free. Where? At skytourlive.org, right here. You go there and it will tell you where to go for cool pictures. And you can find everything right there. I think you really enjoy this. Look at that. Boy, that's really nice. Let's see how much more is here. Let's pop up, do an instant over processing. Oh, look at that. Look at the tail. There's a knot out here. Look at that.
Yes.
And then there's all this convolution. And look, it's like a fan. It goes this way and this way. Looks like it goes that way and that way. It's got a lot of detail in this ion tail. Extremely interesting. Let's leave that for now. I'm going to color correct that. And then I'm going to drop this down a little bit to soften the noise a bit. Let that normalize. There we go. Wow. The comet's closest approach fantasy, I believe, already happened.
Yes.
And so it's heading away slowly, but look at what it's doing. It's just putting on one heck of a show. And so are the Starlink satellites, unfortunately.
We have that kink or two there, close to the head.
Yeah, right there.
And then there's a pronounced kink farther out, to the upper left.
And we got this. Look at this. This looks like a tail is doing this.
Yeah.
Yeah. And up there, if we could get rid of the satellite trails, we'd see that. But this is the most pronounced area right here. That's why I keep saving this. Because I'm going to make sure that that's preserved in case we get a satellite ripping through there. I'm going to cut down this overprocessing here and pick it up again. Oh, look at that. That's really pretty. Comets are amazing wonders of the early solar system. You know, you're looking at these, you're literally seeing things in the solar system that just were there when the solar system formed 4.5 billion years ago. They're the oldest things in the solar system in general. I mean, not that the Earth isn't similarly old. The Earth's a tiny bit younger than the comets and the icy bodies out in the outer solar system, but not by much. But seeing what's on them shows us all the components, all the chemistry of the early solar system. So I think that's really interesting to look at that.
Michael Hedrick asked a question: do comets often tumble or roll? If you mean the comet body itself, Michael, yes. They rotate. They have a rotation period just like planets and moons and
Yeah.
pretty much everything else. Uh, oh, what was it? Hale Bopp back in the late 90s or 97. If you looked at the comet head at magnification, you could actually see kind of a spiral pattern where the comet, the body itself was rotating and putting off mass at the same time, is making kind of a pinwheel effect.
Hmm.
Looked really cool.
Yeah, this particular comet, um, not this, the Churyumov-Gerasimenko 67P. That comet was a few kilometers in diameter, and I think it revolved once every 7 or 8 hours, if I recall. I might be wrong about that. I think that's what it was. Every 7 or 8 hours. All right, so this is Comet Olbers. Wow. This is just, look at this extra little arch up here. As we get more frames, we have 24 now, and I'm doing it at a gain of 200. And just to remind folks who may not have seen this or don't know, this is our telescope control, this is our telescope computer, this is our telescope view. This is me. This is our stacking window. We're making an image sandwich to bring all the good data to the top. This is the most important field, the exposure, followed by this one, the gain. The sensitivity of the sensor, and how long we're going to expose that sensitive sensor. And together, these two values determine how much noise we get, how many modeling we get. And over time, that goes away. Just like these rocket body images, and this satellite's gone already. This one's fading, and these will eventually fade too, because we're overtopping them with more data as we make more of an image sandwich. This is gorgeous. Look at that. Wow.
Yeah.
I'm going to zoom in on that, because that way we can get rid of these boxy structure. Look at that.
I see several like dark veins coming in from the underside there.
I see this. I see this. I see this. This is really, really interesting. And this red light here, that's the light of sunset, unfortunately. Man, this is something.
Izabela asks, do we recall another comet having such a tail? Yeah. I mentioned in our private chat earlier today, I think, one of the comets we looked at fairly recently, it might have been Pons Brooks. No, within the last year or last 6 months, less. Pons Brooks, because and why we're seeing this happen to Olbers now was the same thing with Pons Brook, is because the sun is at or near solar max, that it's putting out a lot of junk, solar wind and CMEs and all sorts of weird things that are helping break up the comet tail and causing the disconnection events and stuff. Pons Brooks never showed a corkscrew, but Pons Brooks did have some disconnection events.
Yeah.
Like the tail's cut off and then it started again.
Yeah, this, I think the ion tail ends right about here. So that's nice. We're catching the entire tail with some disconnection events. Really something else. And Steven in Belgium, Django, he asks, where to find the t-shirts? Not on Etsy. Yeah, I'm sorry about that. You're right. I've got to get those up there. And where to find the AllSky camera? Oh, I haven't gotten the AllSky camera up there yet, but this is what the AllSky camera is looking like right now. Okay. So that's what we got. We got the summer Milky Way rising. we're looking all the way over in the west over here. The moon is just setting. Okay, but we're way over here. Actually, up here. So we're looking around here. So we're in the kind of the haze, so to speak. But not bad. But if we want to look where we're looking, we're in. See where Regulus is. Regulus and Leo's way down here. Okay. And we are in Lynx, I believe, looking at this particular one.
Yeah, it's up just
Right up,
there's Leo Minor.
right up in here.
And Lynx is very close to Ursa Major up farther to the right.
Uh-huh. I'm looking for Lynx on my constellations. I don't see it. It must be up here. But we're actually quite low in the sky right now. But that's okay. So there we go. And once I get this up online, then we will indeed be able to send you that link so you guys can just always go to the AllSky camera and check it out. Oh, look at this. Look at that.
Yeah.
Now that is fascinating. I wonder if that's
Saw
an
that.
artifact. Let me... Looks too horizontal. That might be an artifact of the brightness. But look at that. Oh my gosh. Let me pump that in and let's see what we got there. Look at all the detail in this tail. Wow. I think we caught corkscrew of a new kind. If it's done it once, it'll do it again.
Michael H. had another question. What was the biggest comet either of us know of? There are big comets, there are small comets. Big comets turn into small comets with repeated passages of the sun.
Yeah.
And since some of them don't come around very often, it takes a long time for a big comet to turn into a small comet.
Yeah.
I've mentioned this before, but when Comet Hyakutake came through in 1996, it was not a large comet at all, but it came quite close to us, so it looked big in the sky. And the next year, in 97, when Hale-Bopp came in, Hale-Bopp was intrinsically a big comet. The nucleus, the actual comet body, was very large, or very much larger than Hyakutake at any rate. And it didn't come that close to us, but because it was so big and so bright, it made quite a spectacle in the sky. There are some comets, I'm trying to think of some of the ones that were real big and they broke up because of the sun. Something's ringing a bell. There's a family, I think, called the Kreutz comets that they've turned into the ones that come close to or hit the sun a lot. There's a whole family of them.
Yeah. Hold on, guys. Hold on, Daryl. I'm going to clear this and start again to get rid of the sunset and to redo it because our comet nucleus is getting a little elongated, and that means our detail is getting elongated. So I'm going to change the exposure time to a full 30 seconds, and then we're going to do this again after I clear this. All right. So there we go, and now we should be able to get even more detail. All right, Daryl. Sorry.
Sorry.
I just wanted to explain what was going on.
Yeah.
Mike Hedrick has a question too. He wants to know what makes a comet a comet. Actually, one of the best questions you could ask, and we have to look at the model of our solar system. In our solar system, we have, of course, the inner planets. We have the asteroid belt, right? Well, we also have a what's called the Kuiper Belt. That's spelled Kuiper, Kuiper Belt. And the Kuiper Belt is a region of very icy bodies out in the outer solar system. And then beyond that, we have the Oort belt. There's an actual belt called Oort, O, capital O, little O, R-T, Oort, named after someone. And then we have the Oort cloud, which is a halo around our solar system of icy bodies. So ice rules in the outer solar system. And so many of these bodies that are covered in ice will have as their core a small asteroid or a large asteroid. And then they get covered with ice and dust over billions of years. And this makes a very interesting show when the comet comes near the sun, because then trapped gases underneath the surface are heated and sometimes pop out, making a bright area around the head of this tiny little rock core that's covered with all this dust and hydrocarbons and carbon compounds and methane and ammonia and so forth, ices. And so that's what makes a comet, and it's called volatiles, things that can be driven off of a surface of a body like this traveling through the solar system. And that's basically the difference between an asteroid and a comet. An asteroid generally does not have these volatile compounds that can be driven off or ionized like this. You're looking at an ionization line of ionized, ions basically streaming behind it. And as I said, these are carbon monoxide ions, CO+. That's how the designation is. So that's what we see. That's the difference between a comet and an asteroid. And I think this red might also be related to this telescope seeing the edge of the building here. It's very dark out there, and there's a little red light, as I've mentioned many times, on the end of the telescope camera, which is in the front of the telescope. And that light, faint as it is, can illuminate the walls of the observatory, because even a small light is extremely visible and truly in the true dark.
You know, that's what they invented black electrical tape for.
Yeah, you're right. You're right. I just never wanted to put tape over that because, and you know, I think Marianne or Tara may have suggested that in the past as well. But I didn't want to put anything over the camera that could accidentally get ingested into the cooling fan.
Yeah.
Because it's right next to it. And let's say it got hot and that stuff fell off. It gets ingested. The camera could overheat and get destroyed. Can't do that. So I'm stuck with this. As it is right now, the camera is set to go to minus 30 degrees Celsius. Oops, sorry. All right. And it's set to go to minus 30 degrees Celsius here. But you'll notice it's only at minus 6. And that's because it's 35 Celsius in the building right now. Almost 36 Celsius. So that's pretty hot. You know. Temperature out there today was 116. And it's probably down to a cool 99 or 100 out there right now, maybe a little more. Look at this. This is something else.
With the new exposure, it still shows all the disturbances in the ion tail down there close to the head of the comet.
Yeah, I'm gonna.
Those kinks and twirls and stuff.
Yep. Yeah, very, very clear. This is going to make a nice processed photo. I'm going to save this because there's nothing in this one for satellites.
Mark, will you excuse me a moment, please?
Yeah, sure.
Right back.
We'll be right here. Very nice. Hey, Marco. Sorry I missed you there. I see you there now. Jessica S. How are you, Jessica S? Petita, I don't know if you answered me when I asked how you doing. Maybe you did and I missed it. I always go back through and read the comments anyway. Let's see if we can sharpen up the detail here. A little bit. That's not bad. Wow, that's nice. Yeah. That's good, Petita. Thank you. Incidentally, next year I will be at Pine Bush in New York. And if all goes well, I'll be at Contact in the Desert again as well the following weekend. Because they moved Pine Bush finally off that weekend, which is great. Fantasy says, no sound in space. Actually, kind of true. In between, bodies out in space, there's no sound. But if you were inside of a star, there's massive sound waves in a star, because that is like a medium through which sound can travel. It's the plasma. And I would dare say it would be darn well deafening. Same thing in a comet's rarefied atmosphere around the coma. You probably could get sound waves transferred through. And if you had a satellite go through that could listen, you might actually hear a very strange music played. And that music wouldn't sound like this, of course. The music would actually be like more like a and that'd be like the interference of the particles moving through this rarefied stream around the comet's head. And Izabela says, I bet if you're inside the tail you'd hear a sound. Well, maybe so. It depends how dense it is. I mean, in this knot here, you would probably be able to hear something, and that's because it would, again, that's actually very, very tenuous right there. The coma nearest the comet is going to be the densest, and I would venture to say it'd be pretty hard to hear it there. See you, Marco. But still, it's pretty cool. Oh my gosh, this is so beautiful. Oh yeah, I'm really I'm enjoying this. I hope you guys are enjoying Comet Olbers tonight. Yeah, we're starting to lose our guiding, probably because it's getting a little bit into the wall.
That's the bummer thing about looking at objects in the western sky after sunset. They go away so fast.
Yeah. Yeah, so I had to raise my full width half maximum filter value a little bit because I failed to notice that the number of exposures were not captured. I wondered why the comet wasn't looking any better. But it's alright. Let me raise this even higher. I'm raising the bar. Good thing I did. It'll be fun to see how this processes out, guys. I'll be showing it to you. I'll make a point of showing this. But you can see the dust tail going up here and the ion tail here. This part of the sky is distinctly a different color than this part of the sky. You notice that? and that's because we're looking at the dust tail. I'm going to pull this back just a bit. And then let's do this. This is called a push. We move these lines close together. And it gets noisier, but you can see what I was talking about. There's the dust tail. And there is the ion tail. I gotta tell you, this is looking way better than it did the last time we looked at it, too.
Yeah.
Wow. We are impacting the wall right now on the far side of the building. So we're going to save this. I'm going to save exactly a scene.
Say goodnight to the comet.
We will, but this is what, if you want to see the comet, this is going to be what you'll see. This is the one that's saved.
Mm.
We're going to process it and make it look as good as we can. Maybe this one will be the one we process. I'm not sure. Let's see. That's pretty too. All right. Well, there we go, guys. That's a really pretty comet. And that's, again, is Comet Olbers. A wonderful comet. And we will put it to bed for the night right now.
Well, I got my wish. I think Izabela got hers too.
Yeah, I mean, Izabela asked for it. You did. So did I. Want to see it. So that's cool. Now, let's see. Yeah, look at the moon's almost setting. And we're actually here in the sky. Look how close to the horizon we are. Wow. Now we run back over this side of the sky and see what we got over here. Oh, let's go up here. I'm thinking maybe... Should we do a check-in on T Corridor?
Absolutely.
Alright. T Corona Borealis is known as the Blaze Star. It's a star that actually is a periodic nova star. You'll watch the telescope now swing way up and over as it heads up to the sky. There it goes. And it's going to look for T Corona Borealis. And we're going from way near the horizon. We may have to realign just a bit, but I'm not sure. We'll find out. All right. If you have trouble seeing the star, then it's not T Corridor yet. It hasn't gone nova yet. All right. Yeah, of course. All right. So let's first actually do an annotation. Let's do a plate solve. Find out what is here in the sky in the field of view we've got, and see if we're anywhere near it. And we are. It is right there. So we'll move north. Check it out. We'll do a little bit of a quick stack on it. Just enough to say we did and have a record of it. Okay. And now I'll resolve for this. And we'll get T Corridor pointed out to us down low. There we are. And now we'll head to the west a little bit. So far, it has remained like it's behaving itself, which is good. And then we'll move south a little bit to, it's right here. All right, so the annotation will we just leave on for now because we have to redo it every time we move the telescope. Hello, Cynthia Clavey. How are you? Connie, are you going to bed? Is that what you're saying? Connie Quake saying goodnight? I don't blame you. It is kind of late, isn't it? All right. So let's do now that we know this is the Blaze star, we're going to drop this off the list. We don't need to look at that. And now we'll do a 12-second shot. All right. And we'll go into deep sky mode. And here we go, deep sky mode. And we'll see the last view of the comet, which is already up on the server, no doubt. All right, and now we'll see T Corona Borealis, which is this nova star. Now, a nova is different from a supernova because this happens with binary stars that have a companion. And this particular star right here has a companion. This is a red giant, actually, and it has a companion star that was similar to it. And the companion star that was to this one grew into a red giant previously, and then shrunk down to a white dwarf. And then this star was leaking as it went to a red giant. It was leaking gas onto the surface of the white dwarf, and it takes about 80 years, and it reaches a certain point where the thickness of the hydrogen gas that's now laying on this white dwarf becomes enough that the underside of that layer gets hot enough to start fusion. And when that happens, the star goes into runaway fusion on its surface. And it's nothing that will destroy the star, because the star's mass that it's acquiring is not more than 1.44 solar masses, the magic Chandrasekhar limit number for white dwarfs blowing up with the star when that happens. So it's less than that, and so the star ends up just expelling a lot of light as it goes into this runaway fusion, and it lasts maybe 3 or 4 days and fades away for another 80 years. And I'll tell you right now, when it happens, we're going to catch it. We're going to look for it. But this is the guy. And if we bring up our annotation, I'll save the image with annotations right now. All right, there you go. So now that'll be saved into the directory as well. Although it's going to be saved into the Comet Olbers directory because I forgot to change it. I'll just do it all again. T-Core Bore. Then it's going to say, do you want to change it? Yes. Yes, I want this changed. Okay. And now we'll save it again.
Izabela, Ray. Estimates I've seen, it's presently at 10th magnitude. And if and when it goes nova, it may go up to 2nd magnitude. We've shown you the star Alphecca before, also known as Gemma, in Corona Borealis. Just like the jewel in the crown, it's the brightest star in Corona Borealis, and it is 2nd magnitude. So instead of 1 jewel for maybe a week or two, Corona Borealis might have 2 jewels in it.
Yeah, for a period of time, for about 3 or 4 days.
Yeah.
Okay, we got 14 frames. I'm going to go to 15 and we'll save it. I renamed it properly now. I'll fix that on the server later. Okay. Let's also do this. Let's bring this to the peak. Alright. And then move this down. This is T-Core Bore. We do this to see it. There it is. Alright, and then we'll save it again. Color correct first. Alright, and we'll save. And save exactly as seen. Okay. All right, that's our check-in on T Corona Borealis. And let's now go and look at another object that might be available to us right now.
I saw an interesting video today on YouTube.
Did you?
Yeah, it's one of those Sabine Hassenfelder
Oh yeah, Sabine.
videos, and I'm a hillbilly. We say Sabine. She was talking about cosmic or cosmological redshift and time dilation,
Okay.
how they go together, and some parts of what she said made sense and seemed obvious. Some of it I was having a little trouble getting my head around.
Do you remember what she was saying?
Basically, that in the far past, time moved slower than it does now. And that was the part I was having trouble with. Then she said that, well, even though time moved slower in the past, anybody back then wouldn't have known any difference. You know, it was just a normal passage of time. And the one part she said that did make sense to me was the old thing, if you fall into a black hole and somebody watches you, that from your point of view, yeah, you fall into the black hole and cross the event horizon and disappear inside.
Yeah, they never
But
see it happen.
to the outside, to an outsider, they would never see you actually reach the black hole. You would just kind of freeze.
Yeah, at the surface of the
get
event
close.
horizon, you just stay there.
Yeah.
All right, let's try this.
And she said it was all the same thing. And I mean, I've heard that part and I understand that part. But,
Yeah.
the part about, I mean, if time, she said time is moving slower in the past. I think that sounds more like still a point of view thing, you know, that because of the redshift, because we're seeing the redshift, well, the time slowed down from our point of view in the past. Not that it necessarily would have to anybody back then.
Okay, this is the star called Alniyat. Alniyat. Alniyat is northwest, of Antares in Scorpius, the Scorpion. And it has this amazing nebula right here that I want to show you. And we're going to get there by heading east and centering up Alniyat a little more. I'll leave Alniyat a little to the left because that's going to be better to show this nebula. Alright, so I'm going to pop us back just a little bit.
Fantasy, Sabine, she made the point that it's all Einstein's relativity. I don't recall ever hearing them talk relativity in Star Trek. But it's all reference frames, you know. I mean, me seeing you fall into a black hole, well, from your reference frame, yeah, you fell through the event horizon. From my reference frame, I never see you quite reach the event horizon, or pass through it at any rate. It all depends on where you're coming from, so to speak.
That's right.
I don't know that they ever got into that in Star Trek.
No. They never went down that path. Okay, we're going to come out of low light mode and go into our stack mode here, our deep sky mode. And we're going to remove T-core bore. And I'm going to change the name here. This will be Alniyat. And you will see this nebula very, very obviously. It's a beautiful nebula. Lots of detail. It curves around the star. Here it is. Look at that. Now what we'll do is we will process a little bit like that. And let's do this. Now you'll see it even better. So we'll go bring this black level up to the average of the red, green, and black curves, which is this white curve. And then we'll just let this sit here and percolate. That halo we see around bright stars, because we're running the telescope 25 times faster than its native construction had it running. OG Skywatch, how you doing? OG says, the cryptoterrestrial hypothesis, case for the scientific openness to a concealed earthly explanation for unidentified anomalous phenomena. Well, I've heard that, quite a lot actually. Many over the decades I've been doing this for a long time. I've been hearing people saying that there is a more terrestrial explanation for unidentified aerial phenomena, or UFOs as people call them. And I, as a science guy, I can't sit here and be arrogant and say, no, that's not true, they're aliens. But I will say that it's in all likelihood, it's going to be something that is out of our daily experience for sure. And as far as I'm concerned, there's no reason it cannot be extraterrestrial life. We stand out like a sore thumb, we always have. Because if most likely life in the universe is based on carbon, as I've said 1,000 times. That makes me a carbon bigot. I've said that a few times too. And as a carbon bigot, I know that oxygen is required for carbon-based life to thrive and process and metabolize and oxidize the daily chemistry that goes on inside the carbon-based body. And because of that, I say that because there's oxygen in our atmosphere, any civilization that's carbon-based, that has an interest in looking in the night sky for other homes for themselves or other worlds like theirs, they're going to find us. Because we have a copious amount of oxygen in our atmosphere, and we've been pumping it in there ever since 2.5 billion years ago during the Great Oxidation Event, the GOE, where phytoplankton in our early oceans began pumping oxygen into the atmosphere as a waste product, by the way. You're breathing plankton poop. Yes, you are. Okay, so that said, I have a feeling that people who would like to suggest that no life could find us, I beg to differ. We have been very obvious to the universe for roughly 2 billion years. So we're looking for other civilizations like ours right now, and we're looking for oxygen in an atmosphere. So keep that in mind.
Mars needs women.
And then there's that. That's right.
That reminds me, though, today or yesterday, depending on what time zone you're in, was not the day that the Roswell crash happened, but it was the day that the Air Force said it was just a weather balloon.
Yeah. Was that the date of the photograph in the newspaper where they're holding the remains of some weather project?
I I didn't see that particular mention. This was just a little blurb over on, daily factoids over
Okay.
on Wikipedia.
Well, I can get the answer directly because Barbara Beck is the owner of the Roswell Daily Record, the newspaper that broke the story, and it was her family that broke the story. And I know Barbara very well, and I could ask Barbara all the details on that, and she will be more than happy to supply them, I'm sure.
Yeah, well, the 8th was the day the official explanation came up.
Yeah. OG Skywatch says, I was stoked to see Harvard taking it seriously. I assume Avi working there helps the cause. Yeah, I know Avi. We're friends. And I'll tell you this. Avi Loeb was taking a lot of heat for saying that Oumuamua could have been alien. He didn't say it was. All he said was, we can't deny the possibility that it was. And then he did that search in the ocean, the maritime search for those nodules on the ocean floor, and said, they're interesting. He's not saying anything incorrect. He's not making radical conclusions. He's saying we can't deny the possibility. Now, the latest thing Avi's been talking about is something I've been talking about. And the last show that we did together was an ABC special, but in that show, I talked about interdimensional travel and the fact that aliens can be traveling interdimensionally. I didn't go through it or describe it. If you want to see that lecture, however, it's on the SkyTour livestream website. You can go and look through the more recent SkyTour radio shows, and you'll find me. I'll be there with Tara Diulis, who is on SkyTour Radio. Daryl used to be. And Tara and I are talking about this, and I actually go through my entire talk on these Kaluza-Klein gravitons that CERN is looking for right now that would allow us to utilize a fifth dimension of travel. We have 4 that we're using now, X, Y, and Z moving through time, but there's a fifth dimension out there, all right? And that fifth dimension is where it's at. And that fifth dimension is linked inexorably to gravity, because when we look at the 4 fundamental forces on our planet, right, we have the strong force, we have the weak force, we have electromagnetic, and we have gravity. Well, those first 3 are covered by the standard model pretty well. And the reason they are is because when you look at the strong force, it acts over a short distance within the nucleus of an atom, and it binds the protons together, all right? It's actually the quarks within the protons that are actually doing the binding, but there's enough force that there's a residual amount of force that holds those protons all together. So it's actually called a residual force if you ever see it that way. But anyway, so those protons are being held together by this strong force. But the strong force originates and ends within the atom. Okay. The weak force is beta decay. That is, it's the ability of a neutron to be captured in an atomic nucleus and then be changed into a proton. And that change occurs by acting on the quarks that make up the protons. Makes up the neutron. There's 3 quarks in a proton, 3 quarks in a neutron, and by changing one of the quarks in a neutron through this beta decay process, again, particles interacting and striking the neutron, it can change into a proton. So you can change, say, a nitrogen atom into an oxygen atom, the next one in the periodic table. Yay, more periodic table elements. All right, so that's that. But that starts and ends in our 4 dimensions, okay? Electromagnetic light, okay? Light is, the electromagnetic force. And it's actually a magnetic field and a electric field perpendicular to each other and propagating. Okay, that's a mind bender when you have to go into it. This is looking nice, by the way. And so the electromagnetic light. Okay, the fields, the electromagnetic light situation. That particular characteristic of the universe, light, starts and ends here. And then we have gravity. those other three are covered by the standard model just fine. And then we have gravity. Gravity, we can calculate its force. It's F equals gmm over r squared. Square the distance between the objects, and you calculate a force based on their masses. That's fine. But guess what? We don't know anything else about gravity, really. Einstein predicted we'd never see gravitational waves. He was wrong. And we have seen gravitational waves with our LIGO detector, one in Louisiana and one in Hanford, Washington, and then the Virgo detector in Italy. All detected these waves passing through the Earth of two black holes that collided. Wow. That led to a revolution because now people were saying, we saw gravity waves. So where's gravity particles? Gravitons. They got to be there, right? Because the thing is, every single previous force I talked about, strong, weak, electromagnetic, within each of those, you can talk about certain elements and aspects of each of those forces as either a wave or a particle. That's called duality. And that's something we see. But with gravity, we see a wave, but we don't see the particle. We think it's also a duality situation, but we haven't been able to prove it. Enter CERN overseas and the Large Hadron Collider. There is a detector on the Large Hadron Collider called ATLAS, just like the Comet thing, but different. And the ATLAS detector is designed to look for gravitons, and a particular kind of graviton that's very, very powerful. And that graviton appears to originate in our 4 dimensions, but end in the 5th dimension. So if you can generate those gravitons around your spacecraft, you're going to get yanked into this 5th dimension, right? And if you get yanked into the 5th dimension, holy cow, think about what that does to you. First of all, let's define this 5th dimension. In this 5th dimension, the farther in you go, that is, the more particles you put around your ship, the farther in you go, and the universe shrinks around you and gets smaller. Okay? So let's say you travel 1 foot in our 4 dimensions. You move 1 foot, you move 1 foot. You travel 12 inches. Now suppose you go into this 5th dimension just a little bit, and you come back. That same 1 foot that you travel in that 5th dimension might have you go 1.5 to 2 feet out here. Oh, neat. Now you say, let's travel 1 foot again, but let's travel way into this 5th dimension to where the universe is highly warped and irregular. And several things happen. Number one, that 1 foot that you travel in this very, very warped dimension, when you come out, could translate to light years. Now, it sounds like crazy science fiction, but it's not. It's actually part of a string theory variation called Randall-Sundrum 1, and it exists. Michio Kaku will tell you about it. Neil deGrasse Tyson will even talk about it, okay? And Avi Loeb will talk about it. And so Randall-Sundrum 1 is this methodology through which interdimensional travel can occur. And if you can surround your ship with enough of those particles, you can literally disappear right before your eyes. True vanishing in the 4 dimensions, because you leave the 4 dimensions. You'd literally see something disappear, and you touch it where it was gone. And then when it comes back, it won't travel the distance from point A to point B. It'll be at point A and then at point B without going the distance in between. Now that's a safe way to travel as long as you know the entry points back into the universe. Because if you don't know those, well, you could pop inside of a star. It's kind of a bad thing. Or in the middle of a planet where you're not able to do the right thing and get out of it. But that's the basic idea. And if you want to see more about that, go to SkyTour livestream with Mark D'Antonio on my YouTube channel and look for that discussion about how UFOs really travel. And that'll be, I forget how long I did. It's like an hour or at least. And you'll see all the diagrams, all the studies, and you'll see how it can work. And then you'll say, wow, now that last question really is answered, right? How could they get here? everybody in astronomy, we all know there's life elsewhere. We all think that. Even Neil deGrasse Tyson, okay? He knows there's life elsewhere. I'm going to tell you a little story about that. But the point... What?
Carry on.
I know, just one more story after another. So the thing is, we all know there's life out there. But the question is, are they here? And through this approach that CERN is now investigating, by the way, because they're looking for these particular gravitons that I'm talking about. And again, the Kaluza-Klein gravitons. So, because they think they're very interesting for reasons I'm going through with you right now. So, now that ties it all together, how they could also be here from far, far away. You know, every observation we see of a UFO in the sky, and the way they move, the way they shimmer and dance around in the sky. Yes, I could talk about, you know, atmospheric scintillation. I could talk about autokinetic effect where your eye can't focus on an object. But as Avi Loeb would say, we can't deny the possibility that we're seeing Kaluza-Klein gravitons in play. So, might they be here? The answer, I think, is possibly yes. You know?
Highly speculative.
Yep, absolutely. You're right. Highly speculative indeed. Okay, I'm going to save Alniyat here. Look at that. That's beautiful, huh? Look at that detail in this nebula. This is really pretty. Okay. And we'll save exactly as seen. Like I said, go to skytourlive.org, go to the upper left to Skytour Livestream, or go to YouTube and search on it. And Skytour Livestream, you'll find it. And it would actually be a very interesting thing for you to see. I think you'll enjoy it. Sam S. String theory does have some caveats in it, and I think that one of the caveats is that you have to convert from thinking of particles to strings, and the way that I tell people this is by saying this: if you look at a proton in an atom, okay, we think of it as a particle, a fundamental particle, and it's true. However, you can also notice that the protons are always vibrating. Everything in the universe is moving at a very, very high vibrational frequency. So if we stop a proton at one end of its travel and then stop it at the other end of its vibrational path and look at what's in between, there's just a tiny, infinitesimally small energy path that they follow. Think of that as the string. So now you talk about strings of energy rather than particles. And this opens up the world of these other dimensions, because now when you're dealing with frequencies, that's what it's all about, okay? And that's why frequencies matter. And that's why string theory is important to prove, which they haven't yet. There are lots of caveats, as you suggest. Oh, Neil deGrasse Tyson, he follows me on LinkedIn, and I thought it was a hoax at first, but then it really was him, as it turned out. He used to say about 5-6 years ago that if you asked him about aliens in the universe or here, he would say, "Oh, there's absolutely no evidence of any of this. There's no evidence." And you know how he can be, okay? Now, you know what? I'm going to share something. He's not an arrogant man, and I know you're going to say, "Yes, he is." He isn't. He's sure of his science, and that makes him come off as arrogant. He won't speak out of his lane. That's the thing. Arrogance, for people who are arrogant, they'll speak out of their lane, and he's never done that. However, since following me and other people, ask him that question about alien life being here, and instead of him saying, "Well, there's no evidence. I don't think they're here at all." He said that, okay? Now what he says is, "I need more data." So in other words, it's a little bit of a difference, isn't it? I need more data as opposed to I don't think they're here. So he's changing his perspective as well. And I think that's a good change for the better. I would ask you, Daryl, if you think that there's alien life here.
Here?
Yeah, from afar. What do you think?
Maybe.
See?
Do I think there's life in the universe? Absolutely.
Sure.
Do I think they're here? I don't know.
But knowing what you know.
I've seen UFOs. I've never seen a flying saucer, quote unquote. I've never seen any little green man or little gray man or whatever. I've never seen a Bigfoot. I don't know. Maybe.
I agree.
I watched
don't...
a lot of Doctor Who.
That's right.
Whatever that's worth. A lot of Star Trek.
Yeah.
It's interesting to think about. Ultimately, for me, it's not fruitful. I mean, it's just idle speculation.
Mm-hmm. There's no doubt. It's speculative.
I'll tell you what I find interesting.
What's that?
I think about this sometimes. Well, if time doesn't pass at the speed of light, like for a photon,
Yes.
that it sounds like that photon, every photon, is in an eternal now. And we may shine a flashlight at the moon and it takes 1.5 seconds for the light to get there, but from the photon's point of view, it took absolutely zero time. Same 8 minutes from the sun to the earth. From that photon that left the sun, it didn't take any time at all.
That's right.
It's always now.
Yeah.
And what is that eternal now?
Mm-hmm. That's actually an excellent thing to ponder, and I'm with you on that. And for those that don't know what Daryl's talking about, it goes to the fact that the closer you get to the speed of light, time slows down. So there's a famous paradox, which Daryl knows about, he's talked about before, called the twin paradox. If you leave and you go out at the speed of light and take a trip to the nearest stars, and then you come back, maybe it took you 6 years to do that trip. When you come back, hundreds of years, if not more, will have passed on Earth. And that's because time for you slowed down. And the time on Earth continued unabated, and you disappeared into history, never to be heard from again, for all intents and purposes, to the people that lived when you left. So a photon at the speed of light would have time that's literally, as Daryl says, it's always now. Now is all it knows. There's no past, there's no future. So when a photon's emitted from the sun, from the photon's perspective, we'll call this, from the photon's reference frame, it's instantly at the Earth where it strikes the ocean, if that's where it was going, or your face when it was there. So the instant it's emanated from the sun, from the core, it's in your face, and it doesn't know any passage of time. Okay, and that's an interesting observation. And where it breaks down is that a photon can't detect changes in time. If it could say no time has passed, but there's no way for it to do that because that construct doesn't exist for a photon. But it's the philosophical question is really quite interesting, especially when you consider that when a photon is emitted from the core of the star or any star, depending on what that photon strikes on the way out, that photon could be absorbed and re-emitted millions of times before it actually gets out of the sun as the original photon. Okay, and so 1,000 years or more could pass before the photon emitted from the core actually makes its way out of the sun. It's not going out unabated. It's actually interacting with all kinds of things on the way out. So is it the same photon? No, but it is a photon cousin that finally gets out, and that's the thing that finally gets here. But to every one of those photons in the line, it's instantaneous from the time of emission to the time that it strikes something. I think that's pretty cool. So that's a good observation there, Daryl, to bring up.
Are all photons in the same eternal now? Is each one in a different eternal now?
It's different. It's a different
Do
one.
they talk to each other?
Now there's a question that's for another physics. We don't have that physics, do we? We can't tell. I don't think that. I actually don't know if anyone's done that. That's probably a cosmological and an astrophysical foray to figure out if every photon that's emitted joins all the rest in now time. I can see Izabela trying to do the table of contents for this. Holy cow, we're just blowing up her brain.
Be sure and hit that like button, folks.
Yeah, if you don't like it, don't hit anything. But if you like it, do please hit the like button. And subscribe if you can. We're having a lot of fun talking about these things. Okay, we're going to go right here. This is good. We've got Alniyat, and 49 is good enough. This nebula is going to make a very, very beautiful image. Okay, so what you're going to get is this image right here. This is the Alniyat image that's up on the server. You can take it down, have fun with it. We also have the raw astronomical file called FITS, which is the flexible image transfer format. Okay. And in astronomy we use that because it's, well, flexible. Allows us to go back and forth and do other stuff we need to with it. Okay. All right. Well, I'll do this one last save, and then we're done. I want to thank you guys for coming out. It was sort of a shorter stream than normal, but that's okay. We wanted to get Olbers, and I wanted to have you with me to do it. So I thought that was kind of cool. Hope you guys enjoyed this and enjoyed Daryl and I going down that foray into philosophy of the photon. Ooh, photon philosophy. That's pretty good, Daryl. Not bad.
I like the comet.
I love the comet. I love those knots in the. I love the knots in the ion tail.
Yeah.
Really, really
I'm glad
good.
we got to see that.
Yeah.
Some doubting Thomas here said we weren't going to see anything, or thought we weren't going to see anything.
Who's that?
I don't know.
Who's the doubting Thomas?
Anyway.
All right, folks. You have a good night.
Thanks for coming, everybody.
Yeah, thanks for coming. Thanks for enjoying our banter back and forth. And hit the like. Please subscribe if you haven't. And you know what? There's other things you can do to help us out as well, because we are a non-profit. We do this out of passion when none of us are getting paid. So check out our Etsy store up there. This is the Etsy store here, and we have taken our photographs and put them on all manner of things. They're on lamps, they're on sneakers, they're on bedspreads, they're on mouse pads, mugs, cups, everything. You can enjoy them and maybe grab yourself something if you want to. Other thing is, too, if you want to join our Patreon, we have patrons. These patrons are absolutely wonderful. They've been helping us. We've got, I see that I'm screwing that up. I've got to move that list. I got to make the list smaller. But we got a number of patrons. We need more. We got to be able to pay for the internet out there. And we have a second site going in Benson. Last show I showed you the Benson Arizona Telescope live. I showed you it's in an office right now in our headquarters, SkyTour headquarters, which is in the house of one of our folks. And it was a beautiful one. We have a new mount for this telescope right here as well, and it's going to be placed on this telescope. We're getting rid of this fork mount, and we're going to go to a very robust German equatorial mount, because this mount you can no longer get parts for, because the telescope company effectively went out of business, so you can't get the original parts. So we'll see you next time, and please do join us and come back and hang with us. And if you want, if you have a mind to, and you like this stuff a lot, consider joining our Patreon. Okay? We would love to have you, and love to have you become a member. There's a value per month for everybody. It's nothing crazy. You can be crazy if you want to, but so much for that. So you guys have a good evening, and Daryl and I will see you on the next go round. All right, and thank you all for coming.
Good night, everybody.
Good night, everybody, and we will see you soon enough. So long.